Welcome to the Deep Dive. Today we're digging into some fascinating research coming out of Alibaba Group's Tongyi lab. They've developed a deep research agent called AgentFounder. Our goal here is to really understand how they managed to get an open source model to compete, well, toe-to-toe almost, with the big closed systems on these really complex autonomous tasks.
Yeah, it's a significant area. We're seeing this major shift, right? LLMs aren't just static Q&A bots anymore. They're becoming these dynamic agents, doing multi-step reasoning, using tools, interacting with environments. And this research tackles a key bottleneck. What happens when you take a standard general-purpose foundation model and try to fine-tune it for these agentic tasks using methods like SFT or RL?
Right, the standard post-training stuff. And the sources say it, well, it doesn't work that well. Performance just isn't there compared to specialized systems.
Yeah.
Why that drop-off?
Well, the core issue is a lack of what they call agentic inductive biases. Your general LLM, it hasn't been pre-trained with the kind of, let's say, inherent understanding of how multi-step processes work. Things like planning, breaking down goals, knowing when to search versus when to rely on its internal knowledge. It has to learn all that and human alignment during post-training. And the research suggests that's just too much to ask at that stage. It creates this optimization tension.
Okay, so it's like trying to build a second floor before the foundation is fully set for that kind of structure. You need something earlier in the process.
That's a good way to put it. And their solution is this intermediate step, Agentic Continual Pre-training, or Agentic CPT. They position it right between standard pre-training and the final post-training or fine-tuning. The whole idea is to bake those crucial agentic biases into the model much earlier on.
So it's about creating a base model that's already geared towards being an agent. Let's clarify the target then. We're talking about alignment, but what does agentic alignment mean in this context? It sounds different from just giving a safe or correct answer.
It is different. Agentic alignment is about behavioral consistency. Can the model act like an expert would when tackling a complex task in a changing environment? That means maintaining a coherent reasoning chain, using tools correctly, and being able to adapt if, say, a web search doesn't return what it expects or a tool fails. It's about the whole process, the operational side.
And the need for this really jumps out when you look at the numbers they provide. You mentioned performance gaps. They cite models like WebSailor getting around 12.0 on BrowseComp, maybe DeepSeek v3.1 hitting 30.0, but then OpenAI's Deep Research Agent is up at 51.5. That's a massive difference.
A huge gap, yeah. And closing that gap is precisely what Agentic CPT is designed for. They laid out two core principles for building the CPT layer effectively. First, the data sources used to train it have to be really broad, not stuck in one domain. Agent skills need to be general. Second, the training data itself must cover a wide variety of agentic behaviors. The goal isn't just mimicking specific workflows, but teaching flexible decision-making.
Okay, so the pipeline looks like take a base model like their Qwen 3 series, do the standard free training, then insert this new Agentic CPT layer, and then do the final post-training SFT. How is that CPT layer structured? You mentioned principles, but what does the actual training look like?
Right, it's a two-stage process within CPT. Stage 1 involves about 200 billion tokens. It's a mix of synthesized agent data and general reasoning data. This first stage focuses on getting the model familiar with basic tool use patterns, reasoning structures, and it operates within a 32,000 token context window.
Okay, 200 billion tokens, 32K context for stage 1, but then stage 2 uses 100 billion tokens, but they describe them as high-quality tokens, and crucially, the context window jumps way up to 128K. Why that massive context for stage 2?
That long context is critical for the kind of deep research tasks these agents are meant for. Think about it. The agent might need to track multiple search results over time, remember previous steps in a complex plan, integrate information from various tool outputs. Without a large context window like 128K, the model essentially starts to forget what it did earlier in the task. It loses track of the plan or the evidence it gathered. Stage 2 is about refining the model's ability to actually use that huge context effectively for complex, long-horizon tasks.
That makes sense. You need the memory to handle the complexity. Now let's talk practicalities. 300 billion tokens total for CPT. A lot of that involves simulating agent actions like web searches or tool calls, the cost of using real APIs for that kind of scale would be astronomical. How do they manage the data generation cost?
That's where their data synthesis methods come in. They knew they couldn't just rely on running real agents constantly. So they developed two main techniques. The first one, focused on volume and cost efficiency, is first-order action synthesis, or FAS. The key thing about FAS is that it generates agent-like data without actually calling external tools or needing direct human supervision for every single data point.
Okay, simulating the agent's thought process based on knowledge it already has, or knowledge they feed it.
Yeah.
How does that work? What's this knowledge-to-question transformation they mentioned?
It's a two-phase process. Phase one is building what they call an entity-anchored open-world knowledge memory. Imagine taking a huge amount of recent, unstructured text data, news articles, web pages, and structuring it. They extract entities like Paris, Louvre, Airbus, and link them to specific facts or statements from that recent data. So the model has access to a kind of dynamic, curated knowledge base reflecting recent information.
So it's like giving the model a constantly updated internal library of current events and facts organized around entities. In phase two,
Phase two, multi-style question synthesis, uses that memory. It samples clusters of related entities and facts to automatically generate complex questions. Questions that might require combining several pieces of information. They aim for diversity factual questions, numerical ones, questions requiring multi-hop reasoning. This creates challenging problem contexts that look like they'd need external tools, but the model can try to solve them using its synthesized knowledge memory.
they give a really interesting example of this, a complex question about the Paris Air Show, right? And it was synthesized by combining three totally separate recent facts about Paris. Something about Louvre visitors, a bug issue in 2023, and details of an Airbus order for 2025.
Right. It forces the model to connect disparate pieces of recent information, mimicking the kind of synthesis a human researcher might do after several searches. And from these synthesized problems, FAS generates two kinds of actions for training data. Planning action synthesis, predicting the steps and maybe the first tool call needed, and reasoning action synthesis, performing logical steps based on the information. Critically, no actual API calls are made, keeping it scalable.
Okay, so FAS gives them volume and covers planning and reasoning simulation without the cost. But real agent interactions, even the ones that fail, have valuable lessons. What about incorporating data from actual tool use? That's the second method, HAS.
Correct. Higher order action synthesis, or HAS, is designed to get the most out of the more expensive data that does involve real tool interactions and supervisory signals, like knowing if the task eventually succeeded or failed. HAS shifts the focus. Instead of just trying to make the model imitate a successful trajectory, it focuses on teaching stepwise decision-making. Why was this action chosen over other possibilities at this specific step?
How do they teach that decision process? You mentioned step-level scaling.
Yeah, so at any point in a recorded agent interaction, a trajectory, they don't just look at the action the agent took. They use the model to generate several alternative, plausible actions or thoughts it could have taken at that step. This expands the decision space dramatically. Instead of just learning from the one path taken, the model sees a whole set of choices.
So it sees the chosen path, but also the forks in the road it didn't take, and learns why the chosen one was better or worse if it failed later.
That's the idea behind the next part, contrastive decision-action synthesis. The model is explicitly trained to evaluate these different options generated by step-level scaling and select the best one. They record the choice made and, importantly, the ultimate outcome of the whole trajectory success or failure, J1 or J0. This turns even failed or suboptimal trajectories into really rich training data about good versus bad decisions at each step. It makes their real-world data go much further.
It seems like a very clever combination. FAS for cheap, large-scale simulation of planning and reasoning, and HS for extracting deep decision-making signals from valuable, real-world interaction data. Okay, let's talk results. Did it work? How did AgentFounder 30B perform?
The results are quite strong, especially for an open-source model. On general agent benchmarks like BrowseComp-en, it scored 39.9%. On the text subset of GIIA, it hit 72.8%. According to their paper, these scores put it ahead of other open-source deep research agents available at the time. It shows that the Agentic CPT layer did indeed boost those core agent capabilities.
And what about those really difficult scenario-specific benchmarks? The paper highlights HLE, humanity's last exam. That one's known for being incredibly tough, needing abstract reasoning.
Yes, HLE is a major challenge. AgentFounder 30B achieved a 31.5% pass at one score. And that's significant because it was apparently the first open-source model to cross the 30% threshold on that benchmark. The sources state it even outperformed reported scores for some very capable closed-source systems on HLE at the time of publication. That's a strong signal about its research abilities.
Wow, okay. And they also tested on frames, which is about multi-perspective reasoning.
Right. Frames test the ability to synthesize information from different viewpoints consistently. AgentFounder 30B scored 89.6% there, again suggesting the CPT process fundamentally improved its ability to handle complex information synthesis, which is key for research tasks.
Beyond raw scores, Did they check if this CPT-based model was actually a better starting point for further fine-tuning, its adaptability?
They did. They ran experiments, RQ2 in their paper, where they took the AgentFounder 30B base model, the one that only went through CPT, and applied 3 different standard SFT protocols, A, B, and C. In all 3 cases, fine-tuning on top of the CPT base model led to consistently better results compared to fine-tuning the original base model without CPT. The average gains were substantial, around 5.75% to 6.45%. So CPT provides a genuinely better foundation.
That seems to confirm the core idea. What about the structure of CPT itself? Did the ablation study show that the two-stage approach or the specific data types were necessary?
Yes, the ablations were revealing. Comparing their 2-stage CPT, 32K context and the 128K context, against a simpler single-stage approach showed the 2-stage method gave consistently better results, about a 3.3% average improvement on pass at 1 metrics. This supports their argument that fully learning from long context agent data up to 128K is really important and perhaps best done in that second focus stage. And regarding data types, RQ4, both FAS and HAST proved valuable. Training only with the synthetic FAS data still gave big improvements, particularly on pass at 3, showing its value for broad coverage. Adding HAST data provided complementary benefits, likely improving the fine-grained decision-making.
And the last piece, scaling. Did this CPT approach make the model more efficient in terms of performance per parameter or size?
It appears so, RQ5. While performance generally increases with model size, AgentFounder 30B seemed to punch above its weight. Its average accuracy across benchmarks, 48.9%, was higher than some larger baseline models cited, like DeepSeek v3.1, 43.0%, or Kimi K2, 29.6%. This suggests that the CPT pre-alignment allows the model parameters to be used more effectively for these complex agent tasks, better scaling efficiency.
So wrapping this up for our listeners, the big picture here seems to be that this Agentic CPT step is a really crucial innovation. By building agentic capabilities into the model before the final fine-tuning, the Tangi Lab researchers effectively created a new, more effective pipeline. They addressed that core problem, the optimization tension, and managed to significantly boost the performance of open-source models on tasks that require deep reasoning, planning, and tool use, making them competitive in the deep research agent space.
It really does look like a foundational shift in how we might build these capable agents going forward. It's not just about piling on more data at the end, it's about structuring the training itself differently.
Yeah.
But there's a final thought worth considering, drawn from their own observations. They mentioned that even with improved agentic skills from CPT, tasks like HLE still heavily rely on the model's underlying reasoning ability to make sense of the information it retrieves. So while CPT helps the agent act better, continuing to improve the core knowledge comprehension and reasoning power of the base LM itself remains a really important direction for future work. There's always another layer to optimize.